Well, folks, good morning, good afternoon, good evening, but not good night, not for at least another hour. Looks like we've got about 30 different countries on board, and I'd like to introduce my colleague and friend, Mr. Matt Davis from QA Systems. Matt?
Hi.
Good morning.
Good to be with you.
Good afternoon for you, I think.
Indeed it is.
Well, folks, software testing is very, very important, and you know how it works. Usually by the end of the project, that's when we start the testing, right? Well, it's too late then. Testing does not improve quality. It assesses quality so we can modify requirements, design, implementation, that's called code, the system, then improve the quality. But testing is vital. When is testing done? Never. When is software done? When it meets the requirements. But you can always test more. The possible test cases are infinite. And all of you have infinite budget, right? If you have infinite budget and infinite time, give us a call. We'll help you on that project, right? Well, you don't. Serious time. You have limited time, limited budget. What are the best practices for software testing? That's the key, okay? So it's 2 minutes after the hour. That's right on time for safety critical projects. Let's go. This is best practices for aviation software testing. And our quick agenda, quick introductions, the usual. We're going to have an overview, 15, 18 minutes on aviation software testing. That means we're going to comply with DO 178, ED 12 over in Europe. DO is document, ED is European document. And then we're going to talk about some challenges in aviation software testing, but challenges are not problems. Challenges have solution. Problems might not have a solution until we make them a challenge and solve that challenge. That's what QA Systems is going to teach us how to do today. They've got about a 25-minute presentation, a demo on how to actually make things work. Not merely theory. We're not getting our PhD here. This is the real world. You got to make it work. So we're going to talk about structural code coverage, requirements traceability, regression testing, test data control issues, automation, efficiency. And then we should have an extra 5-10 minutes for Q&A. We can go a couple minutes after the hour, okay? If you have too many questions, we see some questions already entered, so that's good. Use the question box, not the chat box, if you don't mind. And we've muted your microphones just in the interest of fairness, so you'll have to use that question to pose your questions. If we don't get to your question, we'll follow up with email afterwards, okay? We've got a big group attending today, so popular topic. Real quick, I think most of you know AFuzion. Now, we're a small, big company, big fish in a small pond. We're the largest safety critical services company for aviation in the world. We've got 70 engineers on site doing certification development, many countries. Most of our work's remotely here today due to COVID. I'll be in Spain next week working, but we do a little travel. We do a lot of augmentation, engineering outsourcing, a lot of mentoring, training, certification auditing, EASA, FAA, Transport Canada, CASA, DASA. And we've trained over, that's an old slide, over 30,000 people, which is about 3 times more than all the other trainers in the world combined. About 600 companies use our AFuzion processes, frameworks, templates, plans, standards, checklists, all that kind of thing. Many of you are using those now. And let me turn it over to my colleague, Matt, okay? Matt's gonna give you a nice little overview of his company, QA Systems, okay? And let me make Matt the actual presenter. Matt, you are now the presenter.
Okay, so hopefully I'm sharing the right screen.
There you go.
Excellent. So thanks and welcome all. I'm Matt Davis. I'm the Managing Director at QA Systems based in Bath in the UK. We are a specialist company. So at QA Systems, we specialize in helping companies accelerate their software critical standards compliance through basically a verification-centric approach. So that means our QA MISRA tool provides in-depth static analysis for coding standards compliance. And the one we're talking about today, our Cantata tool provides automated in-depth unit and integration testing. Both the tools support the C and C++ languages and are qualified for DO330 as verification tools for use with DO178 and other appropriate standards. And just so that you know you're in good company, here's a selection of our aviation software customers. So I think that's more than enough from me just as a quick overview. I'll pass back over to Vance.
Thank you, Matt. So folks, let's talk about testing development. It's a fascinating concept, testing versus development. As I mentioned in our intro just a moment ago, development is done when the code and systems meet their requirements. Testing is never really completed. We can always test more, okay? Now, tests. What gets tested in aviation? Easy, only two things. The requirements. Does the implementation meet the requirements? And the code and logic. For safety critical, in aviation, that's DAL ABC for airborne or assurance level 1, 2, 3. It's white box. Look inside the code. Every line of code, data flow, control flow, structural coverage. We'll talk about that. In the old days, we did that manually, and I was one of those monkeys many years ago, decades ago. I'm the old guy here who did that manually. Fortunately, we have tools today, tools like those from QA Systems that will show you. Now, testing in aviation is different than your mother's and father's Microsoft and holding up my iPhone here. Very different from that. There's 4 realms of testing. And if you read between the lines of ED12, or let me share my video so you can see my eyes, DO178 FAA, there's really 4 categories of tests, okay? Functional tests are the requirements. Which requirements? Easy, all of them. System requirements, high-level requirements, low-level requirements, not the architecture. Architecture is part of design. That part of design cannot be tested. It is documented and reviewed, okay? Now, functional tests are black box. See this writing? Functional tests, it's black. We did that to help you remember. Black box. See this iPhone? Black. Yeah, can't see inside the box. However, we also have to look for safety critical, DAL C, AL3 and above. What's inside the box? That is looking at the source code after the requirements page. Don't look at the code to write the test, not initially. If you look at the code to write the test, that's not testing, that is executing. That doesn't find defects. We used to do that in 178B. 178C changed that with some subtleties. So normal range test, the normal operation, you don't find defects there. Those usually work. The robustness test is where we start to find defects, the boundary values, error values, illegal values, state transitions. What about a rainy day? Now, I'm in Los Angeles. You can see the sun outside. It's quite sunny today. We pre-record the weather forecast 2 years in advance. Today will be sunny. Los Angeles is always sunny, but not aviation, okay? Those fellow pilots, yeah, you know who you are. It's the rainy days that scare us. Same with software. The robustness testing is where you start to find the defects. It's white box after requirements-based tests. But the structural coverage is really important, okay? Oh, I had great tests. I covered, oh, I don't know how much of the code. Well, you have to know. And for level C, it's 100%. Level B plus decision condition, level A plus MCDCs. We'll talk about that briefly. The key is to understand why we do structural coverage tests. The answer is a little different than you think. Now, these 4 categories, look at the overlap. There's no gaps. One person's normal range could be another function, because if you have a requirement for it, is it a functional test or a normal range test? Ooh, but there's no gaps. Where you draw the lines is not important. Aviation doesn't have strict boundaries. Those come from your standards. Note the relative sizes. This is a typical, not a great project. Now, black box, white box. They're both important. You could argue black box is more important because if you have great requirements, you will cover 95%. Where does it say that? From working on a few hundred projects. That's what FAA-EASA is looking for. Certification authority. Did you, notice how we switch context? You got to pay attention. Why do we do structural coverage? This is why. Had your coffee? Yeah. Blackbox. We should cover 95% of the logic because we have detailed low-level requirements. At the black box level, functional testing, we're oblivious to the implementation. We don't know if it's code or monkeys inside the CPU. We don't look at it. Test cases come from the requirements, and I hope you have good requirements, but we're going to assess those requirements at the white box level. What has not yet been covered by your great requirements? Well, if you've got more than 15% of the code that hasn't been covered, let me give you a hint. Your requirements aren't good. So these normal range robustness, we look inside after the requirements-based test because those tests look at the code. Now, white box, open the code. My height, my weight. I wore this shirt for you today. It's black. You can't see inside. I'm not taking my shirt off. I'm past that age. Now, to assess my cholesterol level, my cancer, I hope I don't have cancer. You'd have to go inside the box. Abnormal operating conditions, boundary values, add and beyond, air values, illegal values. For example, stress and performance testing. You have a 24 to 28 voltage range. Look at my hands, 24, 28. There's 5 test cases, under voltage, over voltage, boundary, nominal equivalence class. Minimum 5 test cases. If you have great requirements, you got them all. Now, structural coverage, and Matt Davis from QA Systems is going to show you their tool suite in just a moment after we talk some challenges here. It's not quite as easy as we're making it appear here, okay? Coverage is, let me quote from DO, the Aviation Bibles, the extent to which a verification activity has satisfied its objectives. Okay. There's 2 kinds of coverage. Requirements coverage, system, ARP 4754, aircraft and system level. But this is software testing webinar. Have you covered the software high-level and low-level requirements? Typically, there's 3 to 4 low-level requirements per high-level requirement after decomposition, clarification. Then, code logic structural coverage. There's 3 reasons for it. The first one is the popular one. The other 2 are more important. But the official, most important, seemingly, when you read the book is number 1. Did you cover the code according to the rules? Level C, remember level C? Busy passenger, no one can die, passenger injuries, Val C, 10 to minus 5 for a Part 25 large fixed wing aircraft. Raise your hand if you are working. See that little hand sign? Yeah. Raise your hand if you are working on eVTOL or urban air mobility. Okay. Oh, a lot of you. Nice. Many of you. Wow. Not surprising. Well, it's a huge business. It's probably our fastest growing business. But for eVTOL in America, that's a Part 23. For Europe, it's a special condition, similar to Part 23. The reliability is less. We don't have a 10 to the minus 9 function for most of our eVTOL systems, but we still have criticality levels, level B. Level B, passengers can die, but not the flight crew. Ooh, it has a little different meaning for eVTOL, right? The passenger sitting right next to the pilot until we go anonymous. Think about that. Yeah. Unmanned, autonomous, I mean. So, number 2, we have to prove no dead code. Every line of code, every logic statement has a reason to be there. That reason is a requirement, probably at LLR, low-level requirement. But then establish the thoroughness of requirements-based testing. Now, I have 6 children, really. Yeah. The way you get their attention is by yelling at them, right? No, that doesn't work. You lower your voice so they listen. The most important reason for structural coverage is number 3. How good were your requirements and how good were your requirements-based tests? That's official FAA EASA policy. It's in the manual, okay? Number 3 is the real reason we do structural coverage. Now, structural coverage doesn't guarantee quality, even MCDC level A, or assurance level 1 for CNS ATM ground systems. MCDC, proving that each condition independently affects the outcome of a decision when that condition alone affects the outcome. Okay. It's not difficult. It's a toggle test to essentially pseudo-validate the compiler. But MCDC has taken on urban legend as being the best. Automotive copied it. Yeah, ISO 26262. Medical, Sinilac, trains. It doesn't directly improve quality, it assesses the quality. Remember, testing doesn't directly improve quality, it measures the quality. And then we improve quality. So where do we test? If there's a target relationship, or it's DAL-AB, assurance level 1, 2 for ground systems, we have to test on the target. It's safety critical. People can die. So if there's a potential hardware effect, we still have to test even lower DALs or assurance levels for ground. BSP, IO, interrupts, memory, got to test on the target. Simulator, emulator, it's not the real world, but most of our testing is not the target. Most logic is not directly related, affecting the hardware-software interface, okay? Algorithms, logic decisions, exception handling. We can test off the target. Now, testing process. Unit testing is good. Everyone should do at minimum static analysis and developer unit testing, but it tests individual units. Integration testing, that's where we start to really test and put our energies here over here. System level testing is great if we can access all of the software working together. So this is the ideal, this is the practical, and this is what we do for those unique logic cases. The objectives here, take a screenshot of this or look at the recording. We'll make this available, the recording available. We're not going to talk about each of these. We want to introduce Matt in just a moment here. But for each of the levels of testing, we want you to focus on these things. These are not directly in the standards, the guidelines, ED12, DO 178, 278, 254. But this is the implication. When AFuzion does the tests, now you know, this is where we focus. At the system level, we're looking at these system level effects. Take a screenshot, go ahead. Software integration testing. Let's look at the parameter passing. How are the modules really working for data flow, control flow? Can I do coupling analysis? And low-level testing inside the unit. Individual logic steps, input data, responses, sequencing. Okay. Now, the challenges we need to solve, and I'll turn it over to Matt here, we have 6 top ones. Low-level requirements need to be used to achieve structural coverage-based requirements tests, okay? You can't simply execute the code. They have to be based on requirements. That was an addition, one sentence added to section 6 of 178. We need to automate bidirectional traceability. It used to be optional, bidirectional, now it's mandatory. I need to minimize my regression test to show that each change produced no unintended side effects. 15%, according to Dr. Barry Beam, the godfather of software, one of my university professors at USC years ago, says 15% of all changes cause a problem, a side effect, regression test. I need to automate tests. I need to do on-target testing for high criticality DAL A and B, and I need to have sufficient robustness testing, okay? So now, how do we actually solve these challenges? That's the real key. Let me introduce again, Matt Davis from QA Systems. Matt, you are the presenter. Take it away.
Thank you very much, Vance, for that really helpful running of the sort of overview of testing challenges. Let me put this on the screen, hopefully.
Structural code coverage. Vance has outlined why it is used. From our experiences working with aviation software companies, I can give you a few useful hints on what to look for in a structural coverage analysis solution. Firstly, you really need a tool to do the measurement for you, as manual inspection and recording is totally impractical. A structural coverage tool supporting aviation software testing should, of course, be qualifiable under DO 330, but more importantly, should provide easy-to-use analysis for all relevant criticality levels. Our Cantata tool contains predefined rule sets to do just that. Two specifics to look out for here are the non-industry standard definition of the decision coverage metric and whether the tool supports both masking and unique cause definitions of MCDC. Structural code coverage should measure the aggregate execution of code no matter what the test that drives it. As DO 178C notes, it is not necessary to duplicate structural coverage over different test levels. When the test driver is an automated low-level or software integration testing tool, the framework should integrate checks on the required coverage achieved so that analysis is not a separate or manual review activity. During test set development, a code coverage tool can also optimize test cases for equivalence partitions, so only the required minimum tests are used to achieve the required level of coverage. Coverage analysis should provide appropriate support diagnostics and reporting for the whole system to detailed syntax for very specific test cases or test runs, and of course aggregate these over the different tests and executable builds, or even mark code as infeasible for execution in certain configurations to address deactivated Category 2 code requirements, for example. This concept of combining coverage is shown here with a very simplistic system. HIS or software integration tests drive the application code and achieve a certain level of code coverage. Unit B, however, is not executed by this test. So we run a low-level unit test to plug the gap. All of Unit B source code is not built into the executable object code, so not fully executed by our initial unit test on that build variant. Another unit test on a different build variant is run, and the Unit B coverage results combine. Then we have our complete coverage picture. So let me show you how that can be done in a quick aviation software example. Code coverage can be measured and aggregated across different levels of testing. In this short example, for DO 178C level A coverage, we see our system test coverage can be supplemented by unit testing to get the complete picture. Here, the software under test, ARIS, is an open source ARINC 653 kernel simulator, implementing a time and space partitioning concept, with two tasks communicating across a partition boundary running in the ARINC 653 GUI simulator. The Cantata tool instruments the complete application source code to collect coverage during system test execution and produces a standalone coverage file. A Coverage Results Explorer allows us to see the coverage obtained for the whole ARINC simulator application and enables drill down to the syntax details in a coverage viewer for each source file. We see that for one file in particular, 𝑐portservice.cpp, our initial system test, did not exercise much at all. To exercise the logic of this class, we can add a unit test to supplement our initial system level test. Once we've developed suitable unit test cases, we can build and run these with just a few clicks in our test development environment. As full control of the build and execution toolchain is possible, we can switch between toolchains easily to build the same tests for different target architectures to get the coverage across all of them. In this instance, we use a Linux build configuration and run the test binary locally. The combined coverage from our system test and unit test is seen in the coverage viewer. Coverage of 𝑐port service has improved, but MCDC is not fully achieved, as SOC equals -1 is not shown to be effective in the false case. A part of the source code dedicated to a build variant, i.e. not defined as simulation, was not built into the executable object code, so this was not executed in the first unit test. So, as more test cases are needed to execute this uncovered code, we've used the automatic test case generation algorithm to create new test cases in another unit test for the build variant. The code coverage aggregated over these two unit tests and source code build variants demonstrates that 100% MCDC coverage is achieved. With such modern test tooling, you can use best practice code coverage filtering and aggregation capabilities to efficiently achieve the structural coverage objectives of aviation software standards. Aviation Software Requirements Traceability produces the trace data which demonstrates bidirectional associations between all lifecycle data contents, not just to tests. Test coverage analysis is performed using associated trace data to confirm that the test cases exist for each software requirement, but that analysis for high and low-level requirements depends on the software level. In aviation standards, all test cases are requirements-based, so the analysis from the trace data needs to confirm that the test cases satisfy the criteria for both normal and robustness testing. This leads us to consider the granularity of the requirements tracing. The more detailed the requirements, the more detailed the tests can be, and easier to trace to the requirements which they verify. For whitebox testing, this can require explicit definition of the internal code logic as requirements. As Vance mentioned, the code implementation can often further add functional decomposition from even low-level or derived requirements, so their clarity and granularity of test cases is important to the traceability analysis. One final note on granularity, traceability needs to address versions and variants, not just of requirements, but the executable object code being tested, including the use of parameter data. Turning to some practical implications, most of our customers have found productivity, control, and analysis benefits by using dedicated requirements management, PLM or ALM tools. However, it is best practice to avoid proprietary format lock-in with tools that use open data interchange standards such as RecIF. We also recommend data import and export over live tool API connections. It provides write access control to the trace data and separates access to the data from the tool, making IVMV tracing easier and with lower ALM tool license costs. To summarize, bidirectional traceability for aviation software testing is more effectively achieved when testers have full visibility of the requirements and the test cases in the same environment. Importing the requirements data into a test framework is the most effective way to pull these two elements together. In our Cantata tool, this association is made via UI drag and drop with data stored on a local server. When tests are executed, the trace data, along with the test result status, structural coverage achieved, was all exported in the same format to the ALM tool. The thinking work is still needed by a human engineer to confirm the test cases satisfy the requirements, but ALM tools and test tools combined can make that task easier. Let's look at this traceability with a quick example. Commercial ALM tools enable best practices for bidirectional requirements traceability for software verification. This inland 𝘂𝗵𝗶𝗁𝗍𝗍𝗍𝗍 project template provides an excellent starting point to link the standards requirements with pre-configured artifacts and trackers to provide the traceability. We start by setting up bidirectional trace between the low-level requirements and unit tests managed by Cantata. Again, we'll look at the 𝘂𝗱𝗡𝗍 software module. In our Cantata test framework, low-level requirements can be directly imported into the trace view in various formats. We select the RecIF file to make use of the rich data formats supported. A best practice supported by modern ALM tools is the version and variant management of requirements. For traceability, it is therefore important to manage these in respect of the tests which verify them, inheriting or diverging from previous baseline requirements. Comparing imported requirement sets in the test framework quickly enables appropriate mappings to be inherited and changes identified. You can see this in the color highlighting used in the Cantata trace, along with the filtering for precise selections. Selected requirements are listed in the requirements trace pane. Importing requirements in RecIF XML format allows the test tool to present not only IDs or text, but pictures, graphs, and rich media, such as hyperlinks to the 𝘂𝗵𝗶𝗁𝗍 web interface. Intuitive drag and drop maps these low-level requirements to test cases, providing best practice concurrent visibility of both in the same view. Test results, coverage, and mappings are exported back to the ALM tool. Back in the ALM tool, the Cantata test cases tracker shows the verified requirements. Links to test runs show the status of the test, passed or failed, and hyperlinks to Cantata team reporting for detailed test results. Cantata team reporting web interface presents all data for a given test run, including functional test results in the Test Explorer pane, code coverage analysis data in the Coverage Explorer pane, lists of managed artifacts for the test project, and detailed information about the project, variant, timestamp, etc. Returning to 𝘂𝗵𝗶 for the final best practice tip, ALM tools can and should provide a clear visualization and metrics of the achieved passing verification or test coverage status of requirements. Regression testing is simply the process of rerunning previously passing tests to ensure that changes to any part of the software do not introduce errors. In other words, changes have not broken previously working software. Regression testing can be used throughout the development to ensure that changes which do introduce regression errors are detected and fixed early. This helps limit the impact dependency of such errors spreading too widely in the codebase. Aviation software standards such as 𝗂𝗵𝗶𝗁𝗍𝗃 do not even mention the term regression testing, as their focus is on the final required set of software verification results produced by the software verification process activities. However, not only is regression testing widely adopted as best practice, more recently we've seen the growth of continuous integration and continuous deployment and DevOps approaches. The change-based testing approach makes it efficient for very large sets of existing tests to be selectively rerun depending on the scope of the software change impacting a subset of tests. More on that a bit later. Regression testing as part of a CI/CD or DevOps also lends itself to a high degree of automation. Our Cantata test tool and Cantata team reporting tool fit into a CI approach set out by the Carnegie Mellon University here. Beyond automation, regression tests can be run more efficiently when executed with parallelization, whether that involves variant builds of different executable software from the same source code or multiple execution target platforms. Modern build management tools such as Jenkins or Bamboo can be used with test tools to parallelize builds and test runs, along with container platforms such as Docker and Kubernetes. Let me show you that with our Cantata tool as an example of best practice in automated regression testing. Taking a look at the unit tests used earlier, you can see a Cantata test script is written in C or C++ to allow you to easily manage your test cases. In addition to test script generation, the test tool generates a complete makefile build system. This allows tests to be built and executed in various ways. Here we see the existing tests built and executed on the command line for regression testing. Thanks to this makefile system, it's a simple task to use your test projects from within a continuous integration or regression system, like Jenkins here. This Jenkins instance is set up typically where we have an overnight regression suite that completely rebuilds and executes all of the tests in the system. Using the appropriate Jenkins build trigger and the JUnit test visualization plugins, we get immediate feedback on the performance of our regression test suite from within the Jenkins system. We also have a second project here, which is set to trigger on a code check-in so that we can verify tests immediately upon code changes in the system. All commercial test tool vendors should supply Jenkins plugins, which allows you to add a test build step to either new or existing freestyle or pipeline Jenkins projects. And for users of pipeline scripting, it's possible to set up parallelization within your pipeline script to speed the execution of a large test run across parallel executions. As the execution is taking place within your Jenkins infrastructure, it's possible to browse the entire workspace, which will include the test results files that get generated from running your tests. You can drill down to the same level of detail as you can from running individual tests on your desktop infrastructure. So as here, we can see full test case pass and fail results from individual tests straight from within Jenkins. A best practice for regression test automation is ensuring tools provide access to the full certification appropriate results evidence from such regression test runs, as here for Cantata, not only summary data in the Jenkins interface. While useful, Jenkins reports only go so far. Centralizing all test results facilitates another best practice, sharing, across the team or with clients and contractors. Here teams can view current verification status and trends. All test results can be aggregated and filtered by containers and platform execution variants. By drilling down, users can see specific tests, their results, and view code coverage. And coupling this type of dashboard to detail reporting, as in Cantata team reporting here, with CI, teams can share the latest actionable test status management information. One area of aviation software testing often taken for granted is the control of software lifecycle data. A best practice in this area is to ensure the tools used facilitate control of all this data and the validity of the software verification results from software testing. Encryption techniques from tools can play a useful part in this control. A software testing framework can effectively lock down the various parts such as source code, test cases and procedures, makefiles, and options for building and running the executable software, as well as the results produced. For example, in our Cantata tool, a unique hash for each independent asset and report for each test is available. This provides assurance that the test results are completely accurate for the software under test. With built-in tracking of assets using unique checksums, it is therefore possible to automatically identify particular tests to be rerun based on changes to any of the test assets which may affect them. This impact analysis allows for change-based testing to be performed on a continuous integration or DevOps basis, without the need to completely rerun every regression test every time. Regression test runs are therefore faster and optimized only for the changes impacting them. Again, let's see an example. As part of the test build system, Cantata tracks and maintains information on all the artifacts required to build and run each test. Upon project build, an XML file is created with a unique MD5 hash or checksum of these files. This allows tracking of any changes which would require tests to be rerun. Tracking these verification dependencies makes it easier to comply with the aviation software requirements in 𝗂𝗵𝗁𝗂𝗍𝗍𝗍 for software configuration management process activities and definitive recording of software lifecycle data. Aviation software standards require the submission of the evidence of software verification activities on the finally delivered software. However, regression retesting also occurs throughout the development process for changes in requirements or software. This has led to the adoption of change-based testing during a project. The concept is to use impact analysis from a test framework to identify and rerun only those tests impacted by a change, as an efficient way to obtain confidence that regression errors have not been introduced. Such change-based testing is most effective as part of a continuous integration repository branch check-in. The checksums in our Cantata tool, combined with inbuilt impact analysis and guided update maintenance of tests resulting from the software change, are a good example of this best practice. It is not only the test input artifacts, however, which need control, but their output results too. In Cantata, the .ctr log file is the definitive record of test results. The stored checksum irrevocably links the test results from any particular test run to the precise version and state of all its dependencies. Together with the checksummed test input data, this enables all the test data to satisfy the 𝗂𝗵𝗁𝗂𝗍𝗍𝗍 objectives of control category 2. For instance, here in Cantata we have only 2 tests that are required to be rerun because they are impacted by changes to the software under test. This functionality is available in the test framework GUI and on the command line for use with CI build systems.
As you saw, QA Systems has provided good solutions for code coverage, requirements traceability, regression testing, test data control issues. And now it's time for the famous Q&A session. And it looks like we've got about, a good 15-20 minutes, and a good number of questions have come up already. So let's kick over to the Q&A. Before we do, if you have additional questions or needs, just contact AFuzion here, QA Systems. We'll send you some information, and you can join our groups or ask questions there at that time. Let's see, the first question we had is interesting on formal methods. Now, formal methods are formal because they're mathematically based. Languages, C language, English, French, and you know, we Americans, we don't speak English, we speak American. These are not formal languages, but the UK, our British friends, home of QA Systems, by the way, coincidentally, are leading the world in formal methods. It's a search for formal proofs of mathematical closure that we can ensure mathematical closure. When we have that DO333, the formal methods supplement number 4 to 178.278 is what we use also for hardware. So it's a great augmentation, okay, but not a complete solution. So hope that answered it, okay? And both Umid and Nilesh had asked a formal methods related question. So let's see, we have another question for AFuzion here. What percentage, and we have a couple questions there, probably best for QA Systems. We'll turn it over to Matt and Adam Martin to take. AFuzion related question. What percentage of the software testing time could testing take on a project? Okay, good question. Typically, most companies allocate 10 or 15% of the engineering budget to software testing. But A better figure is 25 to 30%. If we look at it, the testing, functional testing, testing the requirements, robustness, structural coverage, all of the regression activity, okay, is going to be over time equal to the actual coding time. So a good breakdown on a val-B, Bravo project, would be about 10% of the time for requirements definition, high level, low level, another 10% for design, less if we're using structured design, more if we're using model-based design, okay, Ccie, Rhapsody, Studio, something like that, no magic. Then we've got configuration management. It's about 5% of the time, even if it's not an independent team. CM, configuration management, is employed by everyone. It slows everyone down a little bit, check in, check out, re-review, ensure no unwarranted changes, track the change history, you know, problem reporting, change control boards. That's about 5% of the project. And then QA. QA is really important. QA is not like Microsoft or Apple QA where they run tests. In aviation, QA does not run tests. Okay, not at all. QA approves the plans, audits performance of engineering requirements, design, code, test with transition criteria, may witness some subset of the tests. Okay, that's undefined. It's in your QA plan for aviation. But about 5 or 7% of your budget, so one QA person to every 15, 20 people, is required to do that, to do those audits. Remember, QA doesn't review, it's audits. Engineers review, thorough, technical, broad checklist. QA audits, especially transition criteria. Then reviews. Reviews are part of verification. They're in your software verification plan. That's about 10% of the time you'll spend doing requirements design code reviews. And then the actual testing itself is, as I say, 20 to 30%. That's the remaining budget. It's quite a bit of time because of all the reruns, the regression test. All the more reason you need to use, this is the modern world, okay? Software automated testing tools like those that Matt just showed you. Okay, so hopefully that answers your question. Let's see.
Thanks, Vance. I think we've got another question here about the automated test case generation, which flows very nicely on from your point. Obviously, creating test cases for requirements-based testing, and all of the test cases in DO178 need to be requirements-based tests. Even those that are robustness, driven by structural code coverage, finding gaps, and then retrofitting potentially with additional or expanded, more detailed requirements at the low level. The challenge is creating enough test cases at an efficient level, because there are an awful lot of potential test cases to write by hand. And this is where modern tooling comes in. You saw briefly in the demonstration that I was utilizing some automated test case generation. Tools like Cantata can use automated test case generation, not from word written requirements, because turning English or American words into code and executable test cases and procedures, that's not viable. We ain't got there yet with the AI, but we can interpret the actual source code, derive test cases from the source code to generate framework data, information on what is necessary to drive the software, and determine different paths through the software. Of course, any test cases generated directly from source code, a bit dodgy in aviation, but what it does do is help you plug gaps in particular, especially where you're looking at all the difficult combinations of achieving MCDC and the different combinations of data to drive down the effectiveness of different operands. So we used a little bit of that in the demonstration. We find that the combination of automatic test case generation with requirements traceability actually enables an engineer to use their brain and to validate any test cases that are automatically generated from parsing and generating code. And we have papers and some videos on that might be interesting for people to see afterwards. Okay, Vance, next question maybe.
Very good. We have a question from Susan over in Europe. Susan, good afternoon to you. Question is, what did you mean by requirements-based testing
on code to close the gap? Do we really have to add test cases or requirements? Okay, good question. In the old days, which in technology is, 10 years ago, right? In the old days, the aviation guidelines, DO 278, 178B, said you had to get structural coverage, okay? And that's obvious, but it didn't say how. So India, China, America, Europe, everyone was doing testing. They simply closed the gap in structural coverage by using tools such as those from QA Systems here. But they did it simply by adding test cases, looking at the code, adding a test case, and guess what? It worked. How many defects did that find? Let me give you a hint. 0. Okay. It's executing the code. For example, folks, the old Microsoft, the Bill Gates Microsoft, yeah, the guy whose primary focus was money, still is. Yeah, didn't work so well. You all saw the blue screen of death. Microsoft is changing that. Will no longer be blue. Bad advertising. But Microsoft Windows crashed a lot. That's okay. Windows isn't important. Apple's not important. Help, fire department, my building's on fire. Oh boy, everything's important. Everything's safety critical these days. Well, folks, when you booted up your Windows or Apple computer, you executed hundreds of thousands of lines of Windows iOS code. If you connected a good structural coverage tool, including QA Systems, to Windows iOS, you would show that you covered hundreds of thousands of lines of code. However, did we execute the defects? Oh, that's why we have test cases, requirements, a priori, Latin in advance. What's the expected criteria? Oh, that's what we're checking. What is expected? Okay. Now, we have to think about this. Sorry for the background noise. Got some maintenance going on in the background. We have to instead say, what's the intent of that requirement? We don't get credit just for executing hundreds of thousands of lines of code. It's only by going back and saying, what was intended? Unless you connected requirements and test to those requirements, Blackbox, remember, functional, high level, low level, you don't get credit under 178C. And in fact, Susan, to close those gaps, we actually have to add, requirements first by asking what was missing from the requirement, and then independently for DAL A and B, writing a test case, okay, based on the requirement, re-execute the code and show that then that delta, that additional low-level requirement, accomplished the structural coverage fulfillment. Okay, so hopefully that answers your question.
So just looking at the list here, we've got question on best practice with setting up things for Jenkins and continuous integration. That's a very common thing now. So I would say Jenkins probably massively dominates the market over things like Bamboo and some of the others. So it's an incredibly common mechanism for doing so. We now see quite a lot of pipeline test, or should I say pipeline scripting, used more frequently than the classic setup in Jenkins. We publish a number of videos as well as lots of technical documentation. Everybody should have a Jenkins plugin that allows their tool to work well with that. And so there's further information there. Next question. I think we might have lost Vance for a moment there. So.
Oh, I'm here. Yeah. I just turned off the video.
We lost your video for a second, Vance.
Yeah. No one wants to.
You want to pick up on your next one?
Yeah, sure. So Nilesh asked a question about structural coverage analysis in a host environment instead of a target, and that's a really good question. Now, for DAL A and B, one of the table 6, remember there's 10 tables in 178, 10 tables in DO 278, ground systems, communication navigation systems, air traffic management, copied from 178. Looking at my fingers, I'm holding 10 fingers. I have all my fingers. There's 10 categories of activities in DO 178-278. Plans, requirements, review the requirements, design, code integration, test, review the test, CM, QA, certification liaison. Number 6, verification. For DAL A and B, we need to have Yeah. Target testing, DAL-A adds source object correlation plus MCDC to pseudo validate the compiler, okay, and our makefile setting. But for DAL-A and B, structural coverage, if hardware has an effect, we have to test on the actual target hardware. But as I said during our little training session here about 30 minutes ago, for DAL-C, we can do that in a simulator emulator. We don't have to use the actual target. For DAL-A and B, the hardware software interface needs to be tested on the actual target. So that part of the coverage is going to be achieved at the target. But the rest, Nilesh and everybody, can be done on unit testing, integration testing, off-board, non-target, and get structural coverage. For example, many decades ago, I worked on a 777, Boeing 777 project, and the majority of the structural coverage was done on unit test, low-level tests, okay, for the algorithms, right, but not the hardware software interfaces. So it's a tricky question. You have to know your DAL, development assurance level, okay? Don't get hung up on terminology, level, criticality level, assurance level, development assurance level, design assurance level, DAL. It all means the same thing, okay? The question is, what's the reliability factor from the safety assessment? What's your certification basis? What kind of aircraft are you flying? Big aircraft, fixed wing, part 25. Small aircraft, single engine, part 23, okay? 10 to minus 5, 6, 7, 8, 9, yeah, okay. So hopefully that answers your question. I think that covers our questions, and we're about out of time. Were there any more questions, QA, you wanted to cover, QA systems?
Someone's just mentioned something about qualification of tools. So actually part of the webinar giveaways is some information from AFuzion on these things. Obviously tool qualification kits from vendors are something that are necessary for tools for aviation software for DO178. The DO330 standard has now been separated out from DO178 to basically deal with tool qualification for aviation software. All vendors should supply a tool qualification kit. There's lots of independent advice out there as well in terms of the process. Tool qualification for static analysis and dynamic testing is usually done to TQL5 in terms of the qualification level, because it's not on board or basically a live system piece of code. It's not the code that flies, it's something that helps verify the code, so it has slightly lower qualification level. But I think that probably covers that. So I think that's the end of the questions, in which case we should wrap up and thank everyone.
I think so. And if anyone wants any additional information on tool qualification, they can go to the AFuzion website and download the, the number, DO330, that white paper. Okay, it's complimentary to those who watch this video. So with that, as Matt says, we are done, folks. Congratulations, you're a couple minutes ahead of schedule. Keep that up. Use great tools like those from QA Systems and good services products from AFuzion. You'll be on schedule. Thanks for joining us again, and we'll see you next month for the next technical webinar. Bye, everyone.
Thank you all. Bye-bye.